টুইটে দিয়ে দেওয়া যাবে স্যার, এখন তো চেক করার অপশন এরকম পাবো না আমরা সামনাসামনি।
Yes, I will try to post it in your classroom. I mean, in the LMS, so that you can get it by yourself. Still, I still, I mean, like 15 number of skills I didn't evaluate yet. I'm sorry about the delay. I was very hurried in the last time so that I can show you in this today, actually Wednesday. But once the class is suspended, and then actually I got delayed again. Anyway, don't worry. Since we have an exam, even though we have I mean, yes, I can of course give you, but we hopefully we'll meet again at the end of this month for the sessional quiz purpose, lab quiz. Maybe that is a good day to show you the scripts if necessary. But other than that, I can, the mid scripts, I can give you the mid marks in the that could be available in the website in our classroom, so that you can see.
স্যার তাহলে ওইটা একটু ভালো হয় স্যার, লাইক স্যার 27th যে স্যার ল্যাব কুইজটা আছে ওই দিন যদি স্যার আনা পসিবল হয়।
I'll try, inshallah. Okay, so we have to start. Can you see my screen?
ক্লাস করতেছি আম্মু।
Is my screen visible?
Yes, sir. Yes, sir.
Oh, okay. Okay, excellent. So again, I draw your attention. This is, every lecture is important, of course, but I mean, the last lectures are always very important. All are important, but the last classes, all the classes which are actually conducted at the end, those are even more important, just because we are covering only those part that is important for the exam. So what we are going to cover today, the title is automated planning. Okay, so again, try to understand the problem. So it will be very easy if you listen to me very minutely. Otherwise you feel it hard. Okay, so remember, this is a hard problem. This is the hardest. In fact, this is the hardest problem in the planning area, in the AI area. That is what I am going to cover you today. In fact, my PhD, I started my PhD with this topic. So this is actually, in some universities, even in our time, at our time, this topic was not covered, and in also many universities this is not covered. But even though this is a part of the AI course, but it's a very advanced topic. So that's why I will cover only that part that is easy and convenient for you, so that you can easily appear in the exam. And definitely, if you are serious, I am saying again, if you are serious in today's class, you will feel it very easy, and even you don't need to prepare yourself again before the final exam. This is so conceptual and logical things, and nothing to memorize, nothing. Okay, so hope you can remember, I, at the very first class, maybe in the very first or the second class, I informed you the problem solving. I told you that we are almost wrap up everything. So I told you that the life is all about problem solving. And in order to solve the problem, especially the big scale problem, we have to make use of the AI. So now the AI based problem solving can be categorized into two parts, right? One is the search based strategy, and the other one is the learning-based strategy. But in the search-based strategy, again, there are two types. In fact, three, right? So one was the scheduling-based problem. The other one is the planning-based problem, and other one is the linguistic problem. So I can now hope you can understand. We have already covered all of the part. You should have a very good understanding of everything. So let's for today forget about the learning based problem. This comes from the machine learning, deep learning things. So in this course, we are focusing on the search based code. So the linguistic problem, actually, the first order logic, propositional logic, the way we search the problem, search for the solution, the goal solution, and we prove it using the proof by contradiction, like the inference rule, forward checking, backward checking, etc., etc. And for linguistic problem, that is actually how to solve the linguistic. So in every segment, we covered how to solve and also what to solve. So in linguistic problem, we have covered both the how and the what. So the how part was recently finished in the last class. And regarding the what, is there any modeling? So what to solve means, is there any modeling language? Is there any modeling language by which we can solve it? Yes, using Prolog. One particular example is Prolog, by which we have seen how we can solve such problems using a modeling language. Similarly, for scheduling problem, we also covered it using how to solve and also what to solve. For how to solve, we have used like constraint propagation, arc consistency, local search. These are the strategies by which we can solve the problem. And that is basically the how part. And what about the what part? Is there any particular language by which we can just demonstrate what we want so that it can be solved automatically by the agent? Yes, and that was Minijin. And regarding the planning, yes, we have covered already the what part. Because this is a very elementary way. So, from the very beginning till now, we are mostly on the planning track. I hope you by now you know what is the difference between scheduling problem and the planning problem. So in the planning problem, there is a sequence of action. You have to deal with the action sequence. Already we have covered this, how to solve, like the A star search, SMS star search, IDA star search. There are so many search, even the local search. Those are the search strategies by which we can solve the planning problem, like the tic-tac-toe problem, like the missionary cannibal problem, vacuum cleaning problem, pathfinding problem, eight puzzle problem. So many problems we have covered till now, and how we solve those things. Hope you are very clear about those things. But again, what about the how? Sorry, what? Is there any language by which we can solve it by just representing the problem in that language so that it can be solved automatically? The answer is no. This is what we are going to cover today. And the name of this language is PDDL. Remember, among these three, planning is the hardest problem segment, one of the hardest problem segment. But don't worry, we are not. We will solve the toy problem, right? We are not. We are not. For the sake of the exam and for the basic understanding, we are not going to deal with the complex problem. Just we will try to learn what is. Just the syntax and just. How we can represent these things in some language so that it can be solved. So this is actually today's topic, the language by which we can model the automated planning problem. And interestingly, you can see here the planning algorithm. There are forward chaining, there is backward chaining, there is partial order planning. Well, these are the different category of algorithms. Remember, in the forward chaining, we are actually doing the A star search, different search, etc., etc. And already you are familiar with the forward chaining. I mean, search from the initial state towards the goal state. Backward chaining means search from the goal state towards the initial state. And partial order planning is different, and for now, forget about that. Okay. Um, yeah. So even in your mid exam, we have already covered. So given a state, initial state of an 8 puzzle problem, we have to reach the goal state, and how we can do that using the search. So we know already how to solve these things, right? We have to present the problem using a state space, and then we can apply or different algorithms so that it can search one after another. So can you remember the vacuum cleaning problem? So okay, so what is the vacuum clean? So in the vacuum cleaning problem, we have a state. So we have three variables. Remember what is the state? State is nothing but a set of variables with their specific values. So if you can remember the vacuum cleaning problem, we start with an initial state. And what was the initial state? There were two rooms, and there is a vacuum cleaner. Um, so we have used three variables: left dart, right dart, and the cleaner, vacuum cleaner. So left dart would be, the left dart was empty, means false, means zero. Right dart, sorry, left dart is one. One means true. Okay, we can make it true. Right dart was true. So remember, there was a room like this. There was some dart, and the vacuum cleaner was at some room. So this is room A, this is room B. So we can represent this problem using this state space, using this. So the right dot true, left dot true, vacuum cleaner is equal to left. So this is the initial state. And from here, we can traverse one after another and try to search for the goal. And what are the goal criteria? So the goal is just there should not be any dart in any room. Oh, is it a planning problem or a scheduling problem? This is a planning problem because we don't. I mean, yeah, I mean, you have to show the sequence. In which sequence? Because you from the start state, you have to go from sequence by sequence, means action by action. You need to show us the actions. The solution should be, what is the solution here? The solution is the action sequence. Like go right, clean the dirt, go left, clean the dirt, and done. Something like that. So in this particular problem, what could be the solution? Say, for example, the first stage could be clean, then it will come up to some stage, and then go right, then it will come to an state, and then clean, and then it will come to another stage, and hopefully it will be the goal state. So if we go, say, if we clean the dirt, say at this state, so remember, these are called the action. This is called the action 1. This is action 2, and this is action 3. So if we go right, so what will be the state here? So if you go right, so the vacuum cleaner will be at right. Oh, sorry, this is not the solution, right? I mean, no, this is okay. So if you go right, then left dart is equal to true, right dart is equal to true, vacuum cleaner is equal to right. This is the current state. Sorry. The action is clean the dart. So the action is clean the dart. So left dart should be the left dart should be no or false because already there is no dart. If we apply the action clean the dart, then the left dart will be false. but the right dot will be true, and the vacuum cleaner should be at the left. So this is the current state. And from this state, if we apply go right, then what will happen? Then left dart will be false, right dart will be true, and the vacuum cleaner will be right. And then if we again apply the action, clean the dart, what will happen? Then left dart is equal to false, right dart is equal to false, and vacuum cleaner is equal to right. And this one satisfy our goal. Why? Because we don't want any dart in any row. So since the right dart is false, left dart is false. So left dart should be false, right dart should be false. This is exactly what we want. We don't care about the vacuum cleaner, whether it is at the left room or right room, we don't care. But as long as the left dot and the right dot are false, means empty, that's we are happy and that's the goal. So this is basically the planning problem. Any question till now? What we want to do, we want to automate this problem using a modeling language. So today I will show you just now. I'm going to show you how we can model this problem so that it can be solved automatically by the solver, the backend solver. So in this semester, you came to know a good number of modeling languages. I don't know. You should feel it later on. Well, we understand. We already captured some of the languages, and you can talk to your other friends, even to your seniors also, senior batch. They didn't know this type of language. But these are very important to know. Yeah, I visited some of the international universities during my PhD and other times, and from there I just grabbed this idea that they are teaching these things, and in the AI course this should be taught so that people should also know how we can model the problems. So far you know Prolog, you know Minijig, and today you are going to know the PDDL, Planning Domain Definition Language. Yeah, this is not actually covered in everywhere in Bangladesh. Okay, and really you can apply this in your real life also and in your research, of course. Right. Is it clear, everyone? Just asking. Is it clear to everyone? So far what we have covered. Nothing new we have covered. This is exactly we have covered in the vacuum cleaning problem a long back in the second or first or second class. Yeah, while we are exploring the state space problem, how we can represent the problem using state and how we can search this one after another. Also, we have covered the missionaries and the cannibal problem, how we can represent in terms of state space. Is it clear to everyone? Am I audible?
Yes, sir. Clear, sir.
If you don't respond, then as I told you before, I have second approach of teaching. I can be very fast. I don't care whether you get it properly or not, because even am I slow? If I slow, no response. If I fast, no response. So there is no way to understand whether it's very. It could be the case that it's too naive. I'm very slow. My style maybe might be very slow, so you are not responding. So maybe I could be faster. So if you don't respond, then it's really hard to know whether you are understanding or not. I cannot see you. It's an online class. So should I be faster?
No, sir.
No, sir.
Yeah, then let me know. Okay. I am going to my regular pace. Just interrupt me at any time, but don't tell me at the end, sir. We don't understand. Start from the beginning. I will not start from the beginning. So just catch me at any time if you don't understand, please. Okay. So now let's continue the rest of the part. So this is the planning problem. So why this is a planning problem? Because the solution is a sequence of actions. So what are the actions? Action number 1 is clean the dirt. Action number 2, go right. Action number 3, clean the dirt. And this is the solution. So this is called a plan. So plan is nothing but a sequence of actions that will lead you from an initial state towards the goal state. So that is exactly the definition is here. And what is a planner? What is a planner? Planner is nothing but the solver that actually solve this problem. I mean, definitely there is a so this the planner, the solver, that could be a star search, local search. Those are basically the solver. Nothing but those are the solver. Okay. So now let me straight go to the modeling language. Okay, but before that, one thing I would like to clarify again. I told you before also. So not every time, remember, in order to solve this category of problem, we need to know how to represent the problem, how to represent the state. I mean, how we can represent the state. That is the first thing we should know. In order to represent the state, what should be the variable? I mean, you have to define the variable. You have to define the variable. This is the first thing. And the second thing is you have to define the action. What should be the action? Remember, I didn't define that, okay, the vacuum cleaner, what the vacuum cleaner can do, what my agent can do. It can fly? No. It can jump? No. It can go right? Yes. It can go left? Yes. It can clean the dirt? Yes. So these are the three commands: go right, go left, and clean. So this is called the action. So you have to define the action. What are the actions that can be applied in some state? So that is very important. You have to define the actions. You have to tell the solver that these are the actions that you can apply. And now, once you define the action, there are some extra things you have to mention again so that it can, I mean, the agent can do it automatically one after another. We don't need to specify every time what action you should do or not. So automatically the agent will go forward one after another. And that is for every action. Remember, in planning problem, you cannot apply the action at any state. For example, here, can you apply go left? No, because there are two rooms. Vacuum cleaner is here at the left room. So you cannot go left. There is no left room. Then you will bump with the wall. So this go left will not be applicable. So this is very important. Not every state action, every action is applicable to every state. So how could you know this? So that's why for every action, we also have to define precondition. What is the precondition of an action? So if you want to go left, what should be the precondition? Can anyone tell me? In order to go left, what should be the precondition? So
It
there are
has to
two
be on
rooms.
the right.
Exactly. The vacuum cleaner has to be in the right. And what about the dirt? Is there any necessity of dirt should be there or not, etc., etc.?
No, sir.
No. Exactly. So excellent. So vacuum cleaner is at right. That's so without drawing the figure, we can write straight that the vacuum cleaner is equal to right. Yeah, this is called the precondition. Exactly. So this is what you have to mention. Similarly, sir, what about the clean the dirt? Clean the dirt. What is the precondition of that action?
There has to be dirt in the room.
There should be dirt in that room. Exactly. So this is hope. So excellent. So hope you understand what is the, say, just like you want to go from, say, IUT to Uttara, and now I'm giving you the command, go from airport to Uttara or go from Tongi to Uttara. So you cannot, this action cannot be applied because you are at IUT. How could I give you the action? Hey, go from Tongi to Uttara. You are not at Tongi. In order to apply this action, you have to, I mean, the agent, the robot, the agent, whatever, that agent should have to stay at Tongi. And then I can apply the action, go from Tongi to Uttara. There could be multiple preconditions. Well, I mean, it could be the case that not only the agent is at Tongi, there should also have a car or bus or vehicle at Tongi. So, for example, you are traveling with a car and you are at Tongi, but the car is at Borobari. So again, this is not applicable. Go from Tongi to Uttara is not applicable because you are at Tongi, one precondition satisfied, but the other precondition that the car should also be at the Tongi, that is not satisfied. So there could have a multiple preconditions. So excellent, you understand what is the precondition. Now the other thing. So what I say, you have to define the action, you have to define the precondition of the action, and there are another thing. Once the action is applied, precondition means before the application, before applying the action, what should be the criteria? And there is another thing you have to mention after applying the action. After the action is executed, what should be the change in the variable? What should be the change in the variable? Remember, you don't have to mention those are the same. You only have to mention what changes are done by that action into the variables. And that is called effect. You have to mention the effect. Okay, so what does it mean by effect? What are the changes? Effect means changes. Changes of what? Changes in the state or the variables. Sir, what type of effect or changes? This could be positive to negative, means true to false, that's a change, or false to true, that's a change. But we don't have to mention the same thing. That was true before and true after, then we don't need to mention that. Or that is false before, false after, the execution of the action, you don't also have to mention that. You only have to mention what was true before, but now false, or what was false before and now true. And that is called the effect. So now, in this context, can anyone tell me from here to here, what are the changes? So if I apply the action, clean the dirt at the initial state. So what is the effect of cleaning, applying the action, clean the dirt?
Sir, the left room went from dirty to clean. So there is
Exactly.
no dirt.
Yeah, so the clean, if we apply the action like clean the dirt at room left, then the effect will be the LD, I mean left dirt will be false. That is only the effect. See, you so yeah. So see, this is true and now this is false. But you don't need to mention the right dirt and the vacuum cleaner because these are the same. The right dot was true, now also true. Vacuum cleaning was at left, now also left. So there is no change in that variable. So in the effect, you only have to mention the changes. Similarly, here, if we apply the action from here to here, from this state, if we apply the action go right, what are the changes? So the vacuum cleaner at left, and now after applying the action go right, the vacuum cleaner is at right. So previously it was left, now it is right. So this is the change. So this is called the effect. And you are done. These are the things that you need to know to solve the planning problem using the PDDL. You are already familiar with this, nothing more. And one thing that I can mention, but this is implied, you have to specify the initial state, and also you have to mention the goal criteria. Why I'm saying goal? Remember, I'm saying initial state, but I'm saying the goal criteria, not I'm saying the goal state, because the goal criteria is not this state. This is not the, because the vacuum cleaner could be at left. That is also, for example, left dot is equal to false, right dot is equal to false, vacuum cleaner is equal to left. This is also a goal state. So you cannot mention so many goal state. Rather, it's a good idea to mention just the goal criteria, condition. So what is our goal condition? Say left dot is equal to false, right dot is equal to false. That is, I mean the partial state, partial variable. Only the variables that you, what you want, you have to mention that one in the goal. So hope you understand everything. You are already prepared to see the PDDL or the planning domain definition language. Let's jump into the directly jump into the playground. Means the online solver. Let's go to the online solver. But before that, let me clarify. Let me explain with an example, a very toy example. Can you see the screen? What problem is this?
Tower of Hanoi.
Yeah, so is there anyone who doesn't know about the Tower of Hanoi? I can explain, don't worry. But if you don't know, I can explain.
Yes, sir, we know.
Okay, excellent. Um, just a minute. Uh, okay, so sorry. Um, okay, so in the Tower of Hanoi, this is the initial state, and this is the goal criteria. The goal state. Well, I mean, you can say the criteria only. I mean, this part is the criteria. So you can see from the initial state, this is the action one, and from here, this is the action two, and this one is the action three, and this one is the action four. Oh no, this is not the action four. Yeah. So this way it actually continues, but there is a problem here. So yeah, I mean, what is the invalid action? What actions you cannot apply? So this is what we cannot do. So let me clarify, let me state the problem once again, even though you know it already. So this annotation is getting difficult. That's the problem. Over PDF is okay. Yeah, okay. So this is the initial state, and this is our goal criteria. Initially, there are there are 3 towers, and in every tower, there are 3 things. I mean, there is a base. You can see the base here. This is called the base. This is called the base. This is called the base. And there are 3 disks: disk 1, disk 2, and disk 3. So the disk 1 is smaller than the disk 2. Okay. So yeah. So look at this picture. Yeah. So this is called the peg. Peg means the peg means the base. Okay. This is called the peg. And this is disk 1. This one is disk 2, and this one is disk 3. And this one, as I said, is called the peg. This is called the peg 1 because this is from the tower 1. And from this configuration, this is from, so similarly, this is called the peg 2. This one is the peg 3. So from this configuration, we have to move all the blocks or the disk from tower 1 to tower 2, from tower 1 to tower 2. And the tower 3 is our temporary tower, supporting tower. We can make use of this tower. Now, what are the actions we can apply here? So the action is, we can move the disk from one location to another location. So we can move the disk from one location to another location, remember. Then what is the difficulty here? Yeah, there are some constraints. So there are some restrictions. Not every action is applicable to any action, all state. So you cannot move 2 disks at a time. If the disk is already, well, I mean, okay, the first thing is, you cannot place a smaller disk over a bigger disk. You cannot place a bigger disk over a smaller disk. So for example, the disk 3 cannot be on disk 2 or disk 1, because disk 3 is the biggest disk, the largest, the heavyweight disk, or the biggest disk. So you cannot put a bigger disk over a smaller disk. That is the constraint number 1. And what are the another precondition? This is called the precondition. Remember, if you apply an action, this is called the precondition. Is there any other precondition? So if I say move disk 3, এটাতে লেখাই যাচ্ছে না, খুবই সমস্যা. So if I say move disk 3 from disk 2 to peg 1, it means move the disk 3 from the disk 2. I mean, take the disk 3 from the disk 2 on top of the disk 2, because disk 3 is on top of disk 2. So detach the disk 3 from the disk 2 and place it over peg 2, the peg 2, and place it over peg 2. Is this action is applicable at the first stage? No, because disk 3 is not on top disk 2. So how can you apply this action? This is not applicable. So if you want to move any disk, the another precondition, remember, if you want to move any disk, then that disk should be clear. You cannot move a disk that is already on top of that disk. Some other disks are there. So this is not possible. So for example, in this scenario, you can move the disk red. but you cannot move the disk green or yellow because the red disk is clear. But if I ask the, hey, move the green disk, this is not possible. Move the yellow disk. No, this is not also possible. This is very important. And similarly, yeah. Similarly, this action is not also applicable. This is not applicable. So what does it mean? I mean, move just like say green disk from, say for example, from yellow. I mean, detach the green disk from the yellow disk and place it over the red disk. No, this is not possible. If you apply this action, this will happen. But if you move the green, because for example, the green was here. Okay, so green was here. You move it from here to here. This is not possible. This action is not applicable. If you move the green over yellow or detach the green from the yellow and put it over red, this is not possible because this, what will happen? Because the green disk is bigger than the yellow disk. So you cannot put it over the smaller disk. So the what is the precondition? The bigger disk cannot be kept over the smaller disk. So this is another precondition. So hope you understand. This is the main problem. I mean, we have to move all the disks from one tower to another tower without violating the condition. Now let's see the okay. Just wait. Reading this. Okay, so okay, now we already actually this is difficult to show in tab. Okay, I'm trying to use the tab, but well, okay, so this is the problem formulation of the Tower of Hanoi problem. Okay, first let me show you the description. So see, this is called the Tower of Hanoi problem and how we represent this problem using PDDL. So this is the PDDL syntax. So don't worry about the syntax. It looks a bit weird with so many question mark and etc. But it is very simple once you understand. So already you know everything. And now let me clarify. It would be very convenient if I could write on the screen, but unfortunately, I'm facing some problem from my end. Um, I'm looking for the drawing tool. Okay. Okay, sorry, there is no way. I have to continue this way. Sorry. Okay, so this is the definition of the this is the problem of the Tower of Hanoi. So see, there are three variables here: clear, on, and smaller. I mean, using the clear, you have to mention. I mean, you have to. I mean, in this stage, you have to define what are the variables. So there are three things we need to know about what is clear or not. Something is clear or not. That is what we have to define. But remember, this variable is a variable of variable. I mean, we are not certain. There are. I mean, clear means what disk is clear or what disk is not clear. These things we have to mention. So clear is a predicate. I mean, clear is a predicate means a variable that we have to mention. And the other thing that we have to use as a variable is called on. I mean, which disk is on top of what disk. So remember what we are saying. We have to represent a state in order to, just like the vacuum cleaner. What things we need to mention just to understand the state. In order to understand the configuration of a state, what are the variables or what are the predicates that we need to mention? So in order to see the situation of the current state, we need three things. One is whether something is clear or not. Number two, which one is on top of which one. Number three, which one is smaller than the other one. I mean, these are the things that we should know in order to solve this problem. So this is called the predicate, or you can say it variable. So right. So why the clear there is? So what is variable here? So this is called the variable. The question mark, that is called the variable. Remember, in your final exam, you don't need to worry about. We have to be so very syntax specific. I don't care about the too much syntax, but at least you should know the basic syntax. If you just if your syntax is little bit wrong, don't worry, still you will get the full marks. But I only want to check whether you at least know the basic structure or not. If your structures are okay and mostly the syntax are okay, then absolutely that is fine. So what we are going to solve? The Tower of Hanoi problem. And the Tower of Hanoi, there are three things. Which one is clear? Which one? Remember, in the clear, there is only one parameter of the clear, because we just have to mention something like clear D1. That means disk 1 is clear, or clear disk 2, or clear peg 1. Peg 1 means, say, that the peg of the tower 1. Okay, this is called the peg. So this is how we have to mention the clear things. So these are actually the variables, right? And these are actually the I mean, anything can. These are the parameters that can, any parameter can come. That's why this is called. These are mentioned with the see the. That's why they are given with a question mark. So this question mark means actually the variable, means anything can come in this as a parameter. So similarly, on. So on D1, D2, that means disk 1 is on top of disk 2. Similarly, on D2, D3, that means disk 2 is on top of disk 3. So since D1, D2, D2, D3, this anything can come on top of anything. So that's why the common format is on something X on something Y. So this is what actually have written here. Similarly, smaller. I mean, you have to specify the solver that this disk is bigger than dash disk, that disk is bigger than that disk. I mean, this need to be mentioned, and that is why the third predicate or the variables we have to mention as the smaller. Which one is smaller to another one? That this is very important. So hope you understand. So this is what the predicate is. This is what the predicate you have to mention. Now, regarding the move action, you have to mention the move. So what is the syntax? So you are moving this disk from this disk to this disk. So if I say move disk 1 from disk 2, I mean detach the disk 1 from disk 2 and place it to peg 2. And this is called the move action. And this is called the parameters. See, these are the parameters. And so these parameters are written in this way. See, this one has a parameter, another parameter, another parameter. So these are called the parameters. Again, this is a bit awkward to write in this way, but this is the PDDL style. So you have to write down the parameter first and then specify the parameter. In other language, we just simply write down this way. But here we have to write in a different way. And now what I say, in order to specify an action, remember this is only one action applicable in this tower of an problem. There is no other actions are needed. No other actions are needed. Now, what is the precondition of this action? In order to move the disk from disk 2 to peg 2, you just say what should be the precondition. The precondition is, since you are trying to move the disk 1 from disk 2, then definitely, just like before, the person I am saying go from Tongi to Uttara, the person has to be at Tongi. So if you are saying, hey, move the disk 1 from disk 2, then definitely the precondition should be on disk 1, disk 2. Should be one precondition. Because if the disk 1 is not on top of disk 2, then why you are giving the command, hey, move the disk 1 from disk 2 and place it on top of peg 2. So disk 1 is not on top of disk 2. This is false. This is not applicable. So this is called the precondition. And you see, this is mentioned here. Now, is there any other precondition? Yes. Yes. The other precondition is disk 1 must be smaller than the peg 2. So that means smaller disk 1 there is no clear there is no eraser here, unfortunately. How funny. I mean, annotating over the PDF is fantastic in the tab, but well, I mean, I don't know. Okay, so yeah, so the other criteria, as I said, so the other criteria is the smaller. So since I am trying to move the disk 1 on top of peg 2, so definitely disk 1 should be smaller than the peg 2. I mean, disk 1 should be smaller than the peg 2. So that is actually written here. So the smaller should be written at the right and the bigger should be written at the left. Just like father, X is the father of y. X is the parent of y. The way we just read, you have to write in that way. So exactly, you can see now also that this is also written in some sort of predicates, the propositional, the first order logic style, in a postfix style. Okay, so is there any other precondition? There are two precondition already we have mentioned. In order to move the disk from one, if you want to move any disk from another disk and move on to the and place it onto the another peg or disk. So this is smaller. This is also we have mentioned. Yeah. The other thing is, since you are trying to place the disk 1 on top of peg 2, then the peg 2 should be clear. The destination should be clear, right? The peg 2. So in this case, the peg 2 is the destination. So that's why the clear should be peg 2. See, the clear is disk 2. The destination should be clear. And the last thing, you are trying to move the disk 1. So the disk 1 also should be clear. There should not be anything on top of disk 1. That is also a precondition. If you try to move the disk 1, but the disk 1 is not clear, I mean something is on top of disk 1, then that is not applicable. So that is what also we have mentioned, that the disk should be clear. So these are the four things, four preconditions that must have to be satisfied before applying the actual move. Now, once this is done, now as I said, after the action is executed, what will be the effect? And this is called the effect. And now hope you'll understand by yourself. This is very simple. Once the move action is applied, once the disk 1 is detached from disk and is placed on top of two disks, then this effect will be applied. Sir, how? See, the from disk, is now getting clear, because previously the disk was on top of from disk. Say for example, again I'm giving the action move disk 1, disk 2, and place it to say peg 2. Now if I move the disk 1 or detach the disk 1 from disk 2, then the disk 2 will be clear. Remember that this is what they call from, and this is they are called to, and this is they are called disk. So if I move the D1 from D2, then D2 will be clear. So that is exactly what is mentioned here. Now, what are the other effects? So since D1 after this action, so remember previously the situation is this. Okay. And now we are placing the D1 after the action, and this is the peg 2. So after the action is applied, what will happen? That the disk 2, and here is the there will be peg 2, and on top of peg 2 there will be the disk 1. So what change? Can you see the change from here to here? Yes. One is the disk 2 will be clear. See, this disk 2 will be clear. That is what is mentioned here. And disk 1 will be on top of, so this disk 1 on top of, so see, so disk 1 is on top of peg 2. This was false before. This was not true before, but this time this is getting true. So disk 1 is on top of two disks. The source disk is now on top of the destination disk. This is the new, this is what happened after the action is executed. And any other change? Yes. These are the true. This was previously those are false, and now these are true. And there are two other things that was true before but now false. What are the two things? This one is true, but in this state that is false, and that is mentioned here. The disk one was on top of disk 2. This was true before, but now this is false, and that's why it is written not. And is there anything that is also false? Yes. The peg 2 was clear before, but here the peg 2 is not clear because something is on top of peg 3. And that is also we have mentioned here. The 2 is not a clear anymore. So not means false. Not means false here. Is it clear to everyone? Hello?
Yes, sir.
Any question? Any question here? Apart from the syntax, this is really, really easy. I mean, only the confusing part could be the syntax. Unfortunately, I cannot annotate it properly. This is a bit unexpected. In my tab, there was another annotation, but somehow I need to restart, otherwise that is not pop up. So unfortunately, I am a bit disturbed with this interface. But anyway, with the Zoom annotation I'm trying to show you, I
Sir,
believe this
sir, you mentioned that this will be in the exam. So exactly which
yes.
exam? The AI lab exam or the
No,
final
final
exam?
exam. Final exam. Forget about the exam. I mean, now tell me whether you understand or not. I mean, what part is clear, or if you are still unclear with anything, let me know. So in short, there is a move action, there is an initial state. You know, there could be any state. If you apply the move action, I told you before, there are two things. The one thing should be there should have a precondition that you have to mention in the action, and that is exactly they have mentioned here. If you apply the move action, so this is called the precondition. And after the action is applied, there are some effect, there are some change, and this is the change. This is the change, and this is what we call effect. So this is exactly what is mentioned here. That's it. Nothing extra is written here. Just except the syntax is awkward syntax, but other than that, everything is very same, very clear. So what is the action? Move some disk, say for example, disk 1 from disk 2 and place it to, say for example, anything, say like peg or any variable, this one. If you apply this one, these are the precondition and these are the effect. Done. Now the yeah. So since this is done, the last part is, sir, you have mentioned everything, but what about the initial state and the goal state? What about the initial state and the goal state? So yeah. So this is what mentioned here. This is the initial state and the goal state. Everything is, so now hope you can see here. There is init. So in the initial state, the things are mentioned here. In the goal state, also the criteria, only what we want, that is also mentioned here. So can you go through by yourself? I mean, where is the marker again? It's gone. It's difficult to take an online class this way. Uh, okay, anyway. So see here the initial state. We are mentioning at the beginning that which one. I see. I got it. Yep. Yeah. So this is the initial state, and this is the goal criteria. In the initial state, we are mentioning at the very first. We are mentioning in the initial state. We are mentioning up to this one. We are mentioning which is bigger than what, or which one is smaller than what. Remember, there are three peg: peg 1, peg 2, and peg 3. Peg means the tower, the base of the tower. Because peg 1, peg 2, and peg 3, they are bigger than anything. Remember, this is just the presentation. I mean, you can present in a different way. Not necessarily you have to present in the way I am showing you. You have the freedom. You have the freedom to write your own way. Just like the miniging, just like the prologue. You don't have to write down that the father. You can write down just if. You can write down the father x comma y. You can write down father y comma x. I mean, the way you interpret, the same way you have to write in the modeling language. But what is important here? Can you see all the statements? What you have written here: smaller, clear, on. Nothing new predicates. All the predicates have been declared in the previous slide. exactly you have to use that three predicates, either smaller or clear or on. Apart from these three things, you cannot mention any other predicate. Using these three predicates, you have to define the initial state, and also you have to define the goal condition. What are the new things here? You have to now, this is one particular problem. What was the previous screen? What was there in the previous screen and what is here in the this screen? The previous one is the definition of the action, and now we are defining the initial state and the goal state based on the predicates we have mentioned above the action definition. So now one particular problem is there are three peg 1, peg 2, peg 3, disk 1, disk 2, disk 3. In this particular problem scenario, there could be 4 disks, there could be 5 disks, there could be 7 disks, 10 disks. So that's why there are multiple problems, but the domain is same. One particular domain, but there could be multiple problems. So this is one particular problem. But there are 3 disks and 3 peg. So these are the peg 1, peg 2, sorry, peg 1, peg 2, peg 3. So it means, and there are some disk 1, disk 2, disk 3, etc. So if you look at the problem very clearly, uh, I mean, actually this one is mentioning what is the initial stage. So see, disk 1 is on top of disk 2 is on top of disk 3, disk 3 is on top of peg 1, right? So this is 1. And what about the other 3? I mean, like peg 2 and peg 3. We have not mentioned anything here. Yes, the peg 3 is clear. Peg 2 is also clear. So peg 2 is clear, peg 3 is clear. So basically this is the initial state. So whatever written here, exactly this is the pictorial proof. So then what is this? Smaller, 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 smaller? Because you have to mention, otherwise how the model, how the solver will understand that which one is bigger than the, because D1, D2, D3 it doesn't mean anything. So that's why you have to mention that. You see that disk 1 is smaller than disk 2. So see, yeah. Yeah, see, the disk 1 is smaller than disk 3. Disk 2 is smaller than disk. Oh, sorry. I mean, this is not required. Sorry, this is not required. Even though they mentioned it, this is not required. Forget about this same thing. Okay, so disk 2 is smaller than disk 3. Disk 1 is smaller than disk 2. Disk 3 is smaller than peg 3. So these are just the thing you have to mention. Otherwise, the solver will not understand which one is bigger or smaller. Okay, excellent. Now regarding the last thing is regarding the goal. Now, what is the goal here? See, what is the goal? The goal we are saying, disk 1 should be on top of disk 2, disk 2 should be on top of disk 3, and disk 3 should be on top of peg 3. That means this is peg 1, this is peg 2, tower A, this is tower B, and this is tower C. And what we are expecting is disk 1, then disk 2, then disk 3, and disk 3 should be on peg 3. So this is the peg 3. This is exactly what we want. And that's it. Nothing extra, no new things are there. This is done. And now in order to, now in order to solve the problem, what we have to do? Okay, so first thing is, let me remove 2 extra. Okay, so these are the domain. Already you understand what is domain. And also this is the problem. So in the problem file, there are 2 things, initial state and the goal state. And what are the components what are the objects of the components? So there are, since this is a 3 disk problem, so there are disk 1, disk 2, disk 3, and there are peg 1, peg 2, peg 3. And now if we run it, so see, now I'm going to apply the solver. Remember, we are running it through the online system. So you have to click the solver, and they are now asking for, tell me what is your domain file, what is your problem file. So this is the domain file. See, this is the problem file. And now which solver you want to apply? There are a number of built-in free solvers are given. Already the default solver, best first with search, I mean the FF search, we already applied this one. Let's see. And now start the plan. Right, we already get a plan and see the plan. And this is the plan. You see, we got a plan. So what is the plan? See the action sequence. They are saying, so see, they are saying move the disk 1 from disk 2 and place it to peg 3. The second action is see the action one after another. So this is action number 1, this is action number 2, this is action number 3, action number 4, action number 5, action number 6, and action number 7. After this, you will reach your destination. You can simulate the action one after another, and eventually you will see the solution. You will see the goal criteria. You'll see the goal criteria is satisfied. Sir, what is this thing? Well, I mean, this is just the instantiation. I mean, previously you see the skeleton of the move action, but now once those are grounded, these are the things. You don't need to mention these things. I mean, this is just for the clarification. But this is what the action sequence. This is called the action sequence, and this is called actually the plan. And this is the planning problem. And I'm done for today. It took me a long time just for the annotation things. Otherwise, I could have explained it better. But well, you should go through by yourself. If you still feel any difficulty, feel free to tell me. Even if necessary, I can take another session for explanation. But this is very important. You will be given a problem, a known problem. It will not be very difficult problem, known problem, just like this. And you have to represent the problem in terms of this PDDL. Any question?
Sir,
Yes, please.
I don't actually get why we actually need to use this, because this same problem can be easily solved with Python. You can simply show all the steps to solve the problem in Python as well.
Um, so you are moving from the main stack. I told you before, there are two streams of programming language. One is the imperative way, and the other one is the declarative way. This is the declarative way. I mean, is there anywhere in this programming syntax you have to mention how you solve? Is there any such here? I mean, whatever I have explained here, this is the domain, and this is the problem file. You just mention the problem statement here. Did I anywhere mention the breadth first search, depth first search, A-star search, local search, heuristics? Nothing is mentioned here. Is it the case that you can also do the same thing in Python? Can you write down, can you solve this problem without writing the search strategy in Python? Do you get my point?
Yes, sir.
So that is why every time you are seeing the what part and the how part. I mean, you know how to solve it, it's fine, but you should also be familiar with the modeling part also. I mean, this is the modeling way by which we can represent the problem, and behind the scene, actually, okay, so what you are saying, that this is the solver, and these are the solvers. You can see the list of the solvers. They are actually written in C or C++ or Python. And that is the solving part. But we are not dealing with the solving part today. We are dealing with the modeling part, how to model a problem. That is very important. Is it clear or not?
Yes, sir.
Yeah. So in the exam, you don't need to write in Python. I will not ask you to solve in the lab exam. That's a different issue, because in the lab section we have, I mean, yeah, I mean, we have covered both the solving part in at the very beginning. You have used the normal, you have used the basic Python to solve the different problem using the using like the state space search. you have formulated the problem in two different category. I mean, in the problem formulation and the search strategy, those two things are different. Even in your assignment, that is also given, right? In the lab assignment, you have also used the local search, so you know how to solve these things. But at the same time, we should also know how to model these things. And what is the good thing about this modeling? Once you know we can model this problem, remember, this is a very powerful and very important. And throughout the world, the competition is running. I mean, the competition is not on the last thing. I mean, last minute, I just draw your attention. This PDDL is a very renowned modeling language, but the competition is not about how you model the language. The competition is how much problem you can solve. I can show you one thing. Go to the file, sorry, yeah, file, then go to the load. Oh, sorry, go to the import, and now, yeah, can you see here IPC 1998, IPC 2000, IPC 2002? This IPC is the International Planning Competition. There is a very big competition throughout the world, and so many renowned universities and industries, they participate in this competition, not for modeling, because the modeling part is done by the judge, the chief judge or the judge team. Just like the programming contest in Bangladesh, we only know about the programming contest, but there are many other things happening around the globe. So these they are actually set the problem in this language, modeling language, and now the universities or the other, they actually participate in solving. They build the solver. This is not the case that is an online solver. Just you have to build the solver according to their instruction. You have to submit the solver ahead of the competition, and then your solver will be applied on top of this. So these are the just like the block world. Say for example, you see the IPC 1998, and say there are many category of problem: assembly problem, gripper problem, logistics problem, movie problem. Say for example, we go to the gripper problem and see there are many problems here. Under the gripper domain, there are many problems. So hopefully there are 20 problems here. Yeah. So these 20 problems of different complexity. Problem one is the very small scale problem. Two is bigger than the small. So just like this one, this three disk problem, six disk problem, 20 disk problem, and these were different complexity of problems are there. And those are hosted in this site. And then the solvers, they participate and try to solve. Their code will be executed. We using some script. The script has to be given, and they run the problem. The judge actually run the problem with some automated script, and then they check how many problems in each domain your solver is able to solve, and that way you are judged. And the first, second, third, the different category, they are giving the prize, or they are declared this way. So basically, you can see the solvers. These are the very high profile solvers. You can see some list of the solvers: PFWS, then ENHP, FI, Llama. Llama has you can see the Llama solver. The Llama solver, it was the champion for 3 successive years, 3 successive competition. So these are basically the solvers. Underneath the solvers, there are many complex algorithms are running. They are using local search, A-star search. Underneath, there are so many heuristics to solve this problem. So people are working on the solving part. That's fantastic. But well, I mean, just for the sake of the course, we are actually just for the introducing these things, you need to know how you can represent the problem. Because once you represent the problem in this format, because the good thing is, okay, so the last thing, why this is very important to know, because now we can represent the problem in some way. We don't need to specify all state space. Can you see these things? I mean, we don't need to specify just like the vacuum cleaning problem, missionaries cannibal problem that we have learned before. But this time we don't need to specify all the states ahead of solving. Just we specify initial state and the goal criteria and the action, what action you can apply. And just in the action, we have said these are the preconditions and these are the effects. And the solver is actually apply one action or another action on top of one state. Automatically, it generates the other actions, sorry, other states, and from that states it's repeatedly and with recursively one after another they are applying and search through the state space. and applying the heuristics underneath. So this is the beauty of uh, automated planning and the distinction between the modeling language and the imperative language. I believe you get my answer, get your answer. Any question?
Sir, is this the last class in this course?
Yes, except the one thing remains, but that you can read it by yourself because there is another class on this Friday. But I mean, that will be just one small. Okay, the material already has been covered by your Mahbub sir, and that is the stochastic. Uh, I mean, the probabilistic reasoning. Well, I will give you. This is just a reinforcement learning. I will give you a 30 minutes YouTube video that is good enough for your understanding, and that is enough. Actually, that part is already been covered by your Mahbub Alam sir, and that's why I'm not going to cover that part. Otherwise, I have to take that class on Friday because still I'm not taking any extra class. Well, I mean, at least since there are some of the classes are missed due to some government holidays, so that's why we are lagging behind, and it's really the AI course is syllabus is really big. Okay, so the next class is on Friday, but I am not going to take that class. I will give you a small YouTube video. This is the first time I'm showing you a video, and you should go through. I believe that is very easy. And if you just go through if you just watch the video, it's a just few minutes video, and then you will understand the problem, and exactly the question will come from that video, and that is about the reinforcement learning. Okay, if there is no question further, we
I
can.
had a feedback to share if you just allow me.
Yes, please.
Sir, from the experience of the mid question, what we understood is like these simulations in AI, it takes a lot of time sometimes, though it's
Yes.
simple. And also, sir, there are some questions which need creative thinking. So
Hmm.
sometimes, sir, there are so many questions, and it is very becomes very difficult for us to answer all those questions and all those simulations. So if you just consider that, it will be a little helpful for us.
Yeah, okay. So it is a very fantastic question. Thank you very much for raising the thing since this is almost the last class, apart from the Friday's class. And yeah, I mean, we'll meet again after the Eid vacation. I would explain it again in your lab quiz. But anyway, one thing is very important. This is the AI course. We have to problem solving, just like the algorithm course. This is not the memorizable things. Some things could be creative, but I will not give you anything that is totally new problem. You have to understand the problem from the scratch. One thing is very important. Time, you have to divide the exam time. For example, one question, there could be ABC or only A or B, 1A, 1B, 1C. But for example, the time is 30 minutes. Remember, for question one, you are allotted 30 minutes. So the problem that is given, it takes 2 hours to solve sometimes. So should I spend 2 hours to solve that problem? No. Even though I will not give any problem that will take 2 hours. Just saying, you have to manage the time. So I am not expecting to solve the whole problem. I will see the process. Remember, I will see the process, whether the steps and the process is okay or not, as long as the time permit. For example, the marks is 10, 10, 10. Say, for example, there are 30 marks, 10, 10, 10. So that means 1A, you are getting 10 minutes, 1B, you are getting 10 minutes, 1C, you are getting 10 minutes. So it is in my thought that the student is getting only 10 minutes to solve this problem. So if you cannot complete the problem, solving the problem within that 10 minutes, fantastic. Because I know you have, I mean, I know how to, I mean, whether this is good enough or not. So don't worry about the timing. The only thing you have to, you have to keep in mind that you have to, the time management is important. And in the mid, well, I mean, that was the very elementary problems. And that's why it might be little bit, um, what should I say, like, it feel like so many things to do in just 30 minutes. or 35 minutes. But in the final exam, it will not be that much complex. Don't worry about that thing. But of course, you have to maintain the time. The timing is very important. And again, I mean, you don't need to completely finish the whole all steps. If 10 minutes is gone, just go to the next question. You get my point?
Yes, sir.
Otherwise, otherwise it's really difficult to, I mean, create the questions. I mean, well, I mean, then you have to memorize the things. But remember, with that statement, don't say, "Sir, I have written five sentence, and you should give me the full marks." Remember, the time is 10 minutes. I know how far you can write within that 10 minutes. Yeah, of course, you need to formulate the answer for 1-2 minutes. That is, of course, needed. And the rest 5, 6, 7 minutes, you need to go for solution. And not everything you have to generate from scratch at the exam time. You know the process, you know everything. Just you have to, I mean, in the exam, what creativity might come? There will be no creativity at all. Remember, the only thing that will come, say for example, for today, I'm showing you the Tower of Hanoi problem. And now if I give in the exam the 8 puzzle problem, remember 8 puzzle is even bigger. I will not say the whole thing, but at least for one particular, say for example, in the 8 puzzle, just write down what should be the initial state. So just how you can formulate the 8 puzzle problem in terms of this initial, what is the initial state of this 8 puzzle. So that is the only thing you need to do. So it's not like it's a creative in context of totally new, nothing. You just a whole new things, just like the programming contest, totally unfamiliar things, and you have to draw from the scratch. So what I'm saying, the problem will be changed, but the formula, the system, the algorithm, everything is same. No new algorithm you have to understand. Any further question? Okay,
আচ্ছা,
good. Well,
আমার
yeah, sorry.
বিফোর মিড থেকে স্যার কতটা কোয়েশ্চেন থাকতে পারে অ্যাপ্রক্স, আর সিলেবাস
English
কিছু
in
পুরোটাই
English,
থাকে?
English, please.
ও স্যার,
Foreign students.
বিফোর মিড হাউ মেনি কোয়েশ্চেন্স you will set, and like
I will almost exclude almost everything from the mid exam.
okay sir.
I mean, except one, maybe, but I will mention, I will give you the syllabus, don't worry. Even I will give you the set distribution also. But unfortunately, there will be no alternative because, due to the outcome-based education, we are no way we can give any options. You have to answer all the questions. I don't know, is it a 5 or 6 number of questions in the final
Total
exam?
6 questions.
Total 6. Yeah. You have to answer 6 out of 6. Yeah, but at least I can give you the set distribution. What are from what set? I mean, like 6 sets, and then you have to divide the syllabus into 6 parts. Provided the moderation don't do any sort of modifications. Yeah, and also not only the set distribution, I also will give you some guidance regarding the question. I mean, this type of question will come from this set. This type of question will come from that set. That will also I'll try to give you. So don't worry, go ahead, try to understand the problem. That's why I'm throughout the semester I told you, try to grab the idea. Understanding is very important than memorization. Okay, that's all. Try to go through all the lectures we have done so far. Try to discuss among you. I mean, in a group wise discussion, go for group wise discussion. And still, if there is anything that the majority of you still you are struggling with understanding, feel free to let me know through the CR. Then we can take some short session, and in that session I can make you clear or clarify you regarding it. But I mean, if 120 students ping me 120 times, it's really difficult to explain. But as a whole, in a group wise, I can explain those things. Feel free to tell me, don't worry. But first try yourself. If not, discuss with your mates, and still if you struggle, then let me know. Okay, thank you very much. Here we conclude today's class. Sorry for the delay, it's a long class. Yeah, and the only last thing regarding the Friday's class, I'm not going to take the last Friday class. Rather, I'm giving you the content, just a small YouTube video, and the question will be descriptive question from there. I mean, the question will come from that video. If there is any question, the question will come from that video. That's all for today. Thank you very much. See you, inshallah.